So, my name is Pavel, and I'm the lead architect of our largest Erlang project at Motorola. And Martin is the guy on my team who's smarter than me. And we would like to talk about something that, well, a lot of people supposedly know about, but it's always nice to maybe repeat it a little bit. So, we'll be talking about anti-patterns in the wild. So, mostly what we want to say is the reasons why these things happen, because it's not always that obvious why people write bad code. And then we're going to suggest a few ways of dealing with these problems, and then some kind of methods of how to ensure that if you refactor code, it's still working and you don't have to spend hours and weeks on repairing what you've just done. So just before we go into it, a little background so you know a little bit about the product we're making. Motorola is mostly associated with mobile phones, but that's not really what we do anymore. We do these public safety radio systems for police and firemen and all kinds of public services. We have, if you are in telecom world, you probably know what Tetra is. If you're American, then you will know what P25 is instead. Those are just public safety radio communication standards that we have implementations of. And recently we also went into a little more about LTE and Android apps and this kind of stuff. Ourselves, us two, what we do is we do a little part of a Tetra system that allows you to connect your huge nationwide system to another nationwide system of another country, not necessarily by the same manufacturer. And here's a clip of a Swedish news page that describes an exercise that was run late last year, where Norwegian and Swedish police officers were able to operate together and speak together across two systems, even though Sweden has our competition's system. To give you a little perspective on the product, it's about 183,000 lines of Erlang code in about 531 modules. There is about 89 Gen FSM modules and about 104 Gen servers and a lot of other stuff. We have 71,000 lines of Erlang headers because we have a lot of protocols and a lot of PDUs that need to be defined there. And additionally, we have 7,000 lines of C code because we have to operate with certain hardware components that you just simply cannot operate with in pure Erlang. So there's these two C ports that allow us to talk to these parts. And the whole thing is split into 5 Erlang applications. However, there are kind of 3 releasables, which we sell together as one product. You can't really get one of them only, but it's split up into these 3 servers that we're running. All right, so the way Erlang came in, it started with a prototype many, many years ago. Some of you may know this guy over there. He actually started Motorola, even though he won't admit it today. And he was the one that brought Erlang. So the prototype was run very quickly, was made working, but it was kind of like a rush job to get something to show. Then we wanted to do a real product out of this, and we got a bunch of C developers who have never seen Erlang before to work on that product. And the result is, perhaps you can see here that we have variables named pointer and offset in our Erlang code. And now the product has moved a little bit more into maintenance mode, where we're not really developing any huge new things. However, this time we changed the team again, but this time instead of getting some C developers and telling them, you do this now we actually asked who would like to do something new, exciting, and try something different. So we got a little people who are maybe not as experienced in Erlang, but are definitely enthusiastic about it and want to try it and want to learn. So, moving on. The common specimens of anti-patterns. So we've identified, we have quite a lot of these, or we've had quite a lot of these places, and we've identified some common patterns that kind of repeat themselves over and over in various places of the code. So the main one that maybe many of you have already seen is what we call the shifting state, where we have one function where we have a lot of state transitions and state manipulations within the same function clause. So we have change the state a little bit, then use that in the next function, then change it also again a little bit, then move it onto the next one, and again and again. And I think this is the most we found, which is 6 different versions of the state variable of the Gen FSM until it finally gets out to the next state. So why does this happen? Well, I think the biggest thing is that immutability of Erlang variables is very surprising to people. If you had a C function, you would just have one object that you would just switch change continuously over the course of the function, and then it would exit and it would be the final state. Here you can't really do that, and you have to keep changing the variable names. So you end up with state, newer state, even newer state, my latest state, version 5. And also, our systems are quite complicated, and there's a lot of things that can happen in a single function clause. When you receive one message, sometimes you need to do a lot of things that manipulate the state. A lot of data that you have to remember and save for later. And the protocols are overcomplicated, and the state machines sometimes only compound the problem. And the other problem is that there's just a lot of data to remember. It's a complicated system with thousands of users doing a lot of different things, and all of these things have to be saved for later. So, what can we do about that?
Yes. Hello? Yeah. Okay, so let me stand here, then maybe it doesn't make noise. So now we're going to look at how can we actually solve this. So one thing that we would like to do is to give processes less responsibility. So to give it less responsibility, we look at here one example. So one of the things we had is we have a state machine, and this state machine was handling call controller. So this is some protocol that comes in and some other protocol that goes out again. What this state machine also did was it had some counters to send log messages to remote monitor. So this made a lot of these new state where you just increase counters. And the solution there is quite simple, because you create a dedicated process that keeps track of this counter, and that way you eliminate some states. However, it's not always that easy. So the complexity might be inherent because the protocol is very complex. Also, untangling can be non-trivial, and this might introduce new defects. And this is something that we worry a lot about when we are making our code nicer and we're refactoring. We do not want to introduce new defects. We will talk a little bit about that later. So one other thing is what we can try to do is not on a process level, but when we go down to the function level, there are many functions that take a state in, do something with a very small part of the state, and then return the state. So that you see here on the left. So we see some function F, some function G, and both of them are just manipulating the state. So one thing you can do to prevent having many versions of the state is to rewrite these functions to actually take in exactly what they demand and return only that what they changed. It can be hard to track down what exactly needs to be changed, because these functions might apply other functions that also take the state. So you kind of need to find the bottom of your call tree and then start working your way up. And sometimes after you spend a lot of work, it will only reveal the real state that is needed here. So in the example here on the right, we went from here passing some kind of big state with many things in it, and we don't actually know what each function is changing in it. We now went here to a more specific problem where we see that there was some element of the state that is actually used in many functions, maybe some kind of counter. So even though this makes our code clearer, it's maybe not the final solution, because sometimes you just have something that is used, that is demanded and changed by many functions. So those of you that are Haskell programmers, you probably know about monads. And monads are a nice way. I won't go too deep into monads. I see some people looking very... I won't go too deep into this, but monads are a very nice way to construct computations that change some state. So what we did at some point is we introduced some kind of homebrew state monad. So what you see here, that this is a very simple two-line function. So basically what it does, it takes some state, and then it takes a list of actions, and then it simply maps these actions over the state. And here we give an example of how we use this in reality to make the passing of a state implicit. And the benefit of this is that you always know that the state you get is actually really from the previous action. So we had a few cases in our code where in the beginning you saw state 1, 2, 3, 4, 5, where at some point state 3 was introduced but then actually not used. So some information was lost there. And closer to, yeah, okay. So the information was not used. No, sorry, was the new state. So, for example, state 3 was not used, but instead state 2 was passed in, and that kind of mistakes you can eliminate with this. The problem is you only have one kind of operation. So you take one state in and you return a state. So some people actually thought a little bit more about this than we. And that's the Alendo state monad from the RabbitMQ project. And they not only wrote a library, but they also wrote a parse transform. So that allows you to write a do where you have some manipulations, but it also replaces on a right-hand side expression. You can put in an underscore, which will automatically result in the whole expression being wrapped in a fun that maps from a state to another state. So this is just a little bit syntactic sugar that makes the code easier to read, less boilerplate. What's also nice about this library is that it actually has different kind of operations. So for example, here you see a put, where you only put something in. You don't read something, but you only write. And then you have a modifier, which is the same as before, but you can also return things. So let's have a case study now of some real-world problem we were facing. So this was the first version, as you see. You have here S1, S2, S3, S4, and then we also here have some function which uses the state but returns nothing. Rather, it uses the state for some side effect, which can be sending a message or logging something. Then we also have some operations that might use the state to compute some value which is not the state but rather something else. So here you see party is being computed using the state. And then later we use party again in some other computations. So here we don't need a function that maps from state to state, but rather stores this in a separate variable. And yeah, so it's easy to mix up all these state S1, S2, S3, 4. And we had some real defects on this as well. And you might think, yeah, we immediately notice it. But sometimes these operations only change something in specific cases. So most of the time it might work, but then in some corner cases it doesn't work. So only when you test very thoroughly you will find these ones. So here I applied the Orlando state monad to this problem to the use case I just showed before. So here we do a put again, the modify, which uses state, returns a state, and then here, using this arrow to the left notation, we take the state, compute something from it, maybe use some other input like this macro, and then store it into another variable, in this case party. And then it can also be demanded later on and used. So the benefit of doing this is that the state is managed by the monad, and that way we eliminate mistakes. It's also easier to delete something in it, or maybe add a new line that does some extra manipulation of the state.
So the next one, the long case, which is something probably everybody has seen at least once in their life, and probably the first time you tried to write an Erlang piece of code that had to check for multiple conditions, you ended up with this little monster here. There's two problems in this one. The first one is that the case is deeply nested, and deeply, deeply nested, sometimes even worse than that. The second problem is that there's sequential cases. So first you do this super deeply 5 cases in, and then this returns something which you use in the next 5 cases deep case. This causes issues when you have a clause here, for example, then you have no idea how you got there. It's really difficult to figure out how did you actually get there, under which conditions we get there. And then you have a real world problem where there's a defect in a certain scenario when it happens, and then you have to go through all these case clauses and try to figure out where the hell is that place. So that, of course, again, is a C leftover. I'm gonna repeat that sentence a lot here. A lot of these are C leftovers from people who are used to some kind of if-then statements where you can maybe do this a little nicer. And the other thing is that in C, when you write a function, you don't really split it up into small sub-functions unless there is actually reusability of that function between different places in the code. In Erlang, or in general in functional programming languages, this is maybe not really the case. You want to split this up into as many functions, little ones, as you can. And the other thing is sometimes these cases do certain validation, and they would really like to exit early, because then you realize, okay, we've failed the validation, we should stop right now. In C, it's very easy, you just write return, even though maybe you shouldn't. But here in Erlang or in any functional language, you really can't do that. And once you get into these very nested cases, sometimes you'll have to duplicate the same checks, because regardless of what it is that you're checking, then you need to check the other thing as well. So how do we fix this? Well, there's one way that was attempted. However, it also made this list, so obviously it's maybe not the best way to do it. This one is kind of funny. What it does is it does a bunch of sequential cases, and in case you don't like what you got, then you throw an exception. And then there is a function one layer above that catches these exceptions and does something based on type of the thrown exception. It works, but maybe it's not the most Erlang way of doing things. It also kind of makes it difficult to figure out what's going on. So this was a nice attempt, good attempt, but for somebody who really, really wanted to have a return, but couldn't get one. And it seemed like a good idea at the time, until you need to start changing things in it, and you try to make it a little nicer. So we had to find another solution.
Okay, so here we have a case study of how this can go wrong. We have here a throw used to emulate a C-like return statement. Then some expressions, some case expressions might just be a sanity check that are checking if something is as expected. Or it might store some value to evaluate that's needed for a later evaluation, like the hset variable here. So how are we going to solve this? How are we going to make this nice? We can, of course, try to rewrite it completely from scratch, but you saw how much code we have, and we don't want to introduce new defects. So one thing we tried is a homebrew error monad. Again, we have one type of operation. It takes a state and returns a new state. And also, Alendo had an error monad. So what we do here is we have here, we start evaluation, and we have a case, and when this expression evaluates to error reason, then the rest here is not evaluated. And when it when the result of this case is okay in some value, it will be assigned to this variable, and then the computation continues. So when we look at the comparison, we see that as a side effect of actually making this nicer, also the code gets much more compact. So here we had a lot of throws, and here on the right, instead we made sure to return okay in some value or error and some reason for not continuing. Oh, I went to. So I showed you now some examples of why we maybe want to use Alendo. It has it really gives us some clear code, and this code helps to reduce the chance of introducing defects. However, it is not part of the Erlang release, and especially it contains some transformation of your code. So it's not only a library, but the transformation is tricky because it depends on the abstract syntax tree that you get from the Erlang compiler. So what if that is changed at some point? It also uses some, besides the parse transform, it uses some other undocumented language features. So this means that in production we are quite scared of using Alendo. So I showed you Alendo and showed you the homebrew monad. So at the moment in production we're actually still using the homebrew monads because it gives us some of the nice things of being able to abstract away from using numbered states, away from using throws, but at the same time they are very simple and easy to maintain. So basically what I'm saying is we are a little bit afraid of taking in such a big dependency of Alendo when it's not part of Erlang, and when there's a risk that at some point in time it's all over our code, and then the Alendo team stops maintaining it, and then we need to take it on. So this is a big consideration for production systems.
I think basically what Martin is saying, that somebody should implement monads for Erlang. All right, the next one is the mysterious API. This is the one that probably everybody has seen, and this is the one that gets mentioned every single time, and there's each EUC, there's at least 2 presentations that talk about this. So we have this very nice piece of code that at some point does genfsm send event somewhere to some module. You have no idea which mode. Sure. So when I had to change something in this code, I had to actually, what I had to do is basically search all the files for this pattern here. Luckily, whoever implemented this kept the same variable names, so it was really easy to find which process is actually handling this message. But normally it's not that simple. Also, there's like this mysterious macro that does something, and you have no idea what. Well, actually, this macro only expands into an atom, which is exactly spelled the same as this macro. But that is actually smart. Why is that smart? That's because you can make a typo in an atom, and you won't know until your process crashes. But if you make it a macro, it won't compile if you got it wrong. But it's still, yeah, it looks pretty terrible. and it's a little scary. And I think the way the reason it happens is, of course, GenFSM kind of looks like an API already, right? Why would I need to define any extra APIs when there's already one? That's it. And we've also noticed that, especially when people who are starting or training in Erlang, is that people get really confused who executes what. Which process actually executes which part of the code? Which is the server and which is the client? It's not so simple to grasp immediately. But the solution is also very simple. Define your APIs. So the next one is a little less of a code problem. This one is a little more of a design problem or architecture problem. So we have this process, aptly named coordinator, that does, well, maybe you guessed it, coordinates things. It serves as the process, because we have multiple calls going on, or multiple transactions going on at the same time in parallel in the system, right? However, it's very likely there's only one endpoint at some point. So they all go through the same interface, but they're different transactions. So you have to kind of figure out which message coming from that endpoint is for which of the processes, of which of the transactions. So the way this was solved is that we have a gproc, that's already nice, could be worse, that does a lookup for a key with the transaction ID, and then it gets a PID of that process and sends the message to that process. I mean, it's not a bad solution, right? It's fine, except it does that for every single message within the transaction. So even though you have two processes for each transaction talking to each other, instead of talking directly to each other, they all go through the coordinator. As long as you don't have too many parallel transactions, it's fine. It doesn't matter. But as soon as you start scaling up, suddenly coordinator gets really, really busy. But it is this, why it happens, well, it is the simplest architecture. And it's really easy to implement, and it kind of frees you. You don't have to really think about it. And when the performance requirements put on your product are not so high at the beginning, then you just go, we'll fix it later. But then you maybe have to redesign the whole thing. So it's not actually an easy problem to solve. Not fully. I mean, scalability is, of course, not a simple thing to do. I mean, at the end of the day, we only have one socket at the endpoint, right? So at some point, there has to be something that there will be one process if you only use one socket for all these transactions. You will have to multiply your sockets if you want to parallelize more. But coordinator can be limited. It's easy to do that, at least, where you limit the responsibility of the coordinator process, that maybe it only negotiates between these two state machines that talk together, and then they can just carry on and talk to each other. They don't need to go through the coordinator every single time. gproc is nice to fix it. Helps a lot, but it has its issues. We are a little unhappy with gproc. We don't like the way it throws exceptions all the time and then catches them inside its own APIs. And we also have seen problems where sometimes a process dies but still lingers in gproc for a couple milliseconds, and then you try to look it up and it's there, but it's not. So this actually adds more complexity to what you're doing. You have to be very careful. All right. And then we have a few smaller issues which we grouped together. We have the big module and the big function. This module, you can't see it, but it's 6,675 lines long, which is what? 15 times more than recommended by Erlang coding standards. And then we have a function that is about 321 lines long. So those are hard to read and they're difficult to modify, but I mean, you can live with those. Then we have this funny thing, where we have 3 modules with exactly the same name. I mentioned at the beginning that we release 3 products, which are all part of the same thing, of course, but they're 3 distinct products. And each of them has a module with the same name. And then there's a generic module that always calls an API from that module. It's called NM. So depending on which of the machines this process is running, it will have a different effect. So this is like a funny approach to C# interfaces or virtual functions in C. And then we have this one, which we've ran onto very recently, is that we have a lot of these catch-all clauses everywhere, all over the code, just in case. Because maybe something will return something else. So these usually just come from, a lot of C habits again, because as I said before, in C you like these big functions that enclose a certain functionality. You don't need to split them up, because what for? But also our state machines are very complicated because our protocols are very complicated. We have a lot of messages at the state machines in general, even if on design stage, not even in Erlang yet. They are very complicated with a lot of states and a lot of state transitions. So the state machine just grows and grows and grows until it reaches 5,000 lines. And it is easier to make one process than to split it up, right? Because maybe it starts easy, it starts small, you implement the basic functionality, and then you start adding the corner cases and grows and grows and grows and grows. And once it's grown, now you have a hard time splitting up. And the desire for interfaces, right? So sometimes it would be nice actually to have some kind of a generic way of calling the same function in different modules or something like that to do different things depending on which one is running over there. It's called gen event, I guess, but not always. And this very nice habit of defending against everything. So solutions to these are, well, there's a lot of different solutions. You can try to split it up. You can do a lot of things. Dialyzer actually helps a lot against the last one. I've removed hundreds of clauses like this because Dialyzer said this is never going to happen. So it's very nice to use that. But okay, so we have all these problems and we have some solutions, but that's not everything. So if you're from Denmark, maybe you know these two guys. We have to have some tools so that we can use to somehow fix the problems and help us maintain what we already have. Because the main problem is we are running a public safety business, and we cannot just refactor things for fun. We can't just go in and rewrite half the code base because then everybody will get a heart attack. You can't just release this to a customer that expects, we can't have a fireman trying to press a button on the radio and then nothing happens because we just refactored this little function. It was not a big deal. So we need a way to really validate it. Of course, test coverage, we have a lot of tests, we have unit tests, we have component tests, we have all kinds of testing. But things always can slip through. So we would like to have a method to kind of ensure that what we had is still what we have now is what we had before, or better, hopefully. So what we did is we created this funny quick check model that lets us kind of validate small components of the code that we're refactoring. Doesn't help against huge refactorings, but it does help with like single functions or two functions or something like that. So what you do is you take your code, which you had, the terrible huge function, for example, and then you do some refactoring on it. But then you use our quick check model with some mocking included. You mock everything out, basically. Everything that's not the function you're refactoring, you mock it out. And then you make sure to generate all the outputs, or rather inputs, that will make the code branch off into all possible places. And then you run it and compare. So it looks something like this. We've written this funny thing called equivref. And you provided the pre-refactoring function, the post-refactoring function, a generator that will generate all these possible code paths. Then there's some setup function where you can prepare. We use mech for mocking, so you need to start a few things there, right, and specify some things. And then there's some dynamic things that you also mock out because they depend on what was generated sometimes. So we had this 214 lines of a single clause function. That was everything was in a single clause in one function. It kind of looked like this in UML when we tried to draw it once. This is actually also an earlier version of it, so it's actually a little simpler than it really was. But this function is called in like 5 different states in the state machine, and one of the parameters it gets is a state name, and it then does different things depending on which state it was called in. Very nice. And then it can do a lot of things internally. But after we refactored it, we got it down to, well, 212 lines, so that's not maybe much of an improvement, but that's okay. But now it's 3 different functions, and there's 10 clauses, and each distinct scenario in reality actually has its own clause. So if you only need to fix that scenario, you only fix one clause and you don't break the rest of the code. And no new defects. Nothing went wrong.
Okay, so now we know how we can test that what we made is still right. But maybe we can already try when refactoring to make sure that we don't introduce any new defects. So there are several tools to help with that, and the most well-known one is probably called Wrangler. So this is a semi-automated refactoring. So what you basically do is you tell the tool, I want to apply this refactoring to this part of the code. The nice thing is that the tool can be extended, and that is also necessary because maybe not all desired refactorings are supported by the tool. The problem is it is kind of hard to define how to do this, and yeah, that results in some learning curve. And there's also the question, is the transformation correct? So I have here a little cartoon from XKCD that probably shows our issue with Wrangler. So we would like to use it, but we kind of afraid we get here in the bottom. So we will spend some time writing code, and then the idea is that the code to make refactoring easier will afterwards save us a lot of time. But as far as our experience goes, we actually write something and then maybe it's not quite right, and we spend more time, and then we actually save. So in practice, we have to admit we don't use Wrangler that much. And maybe that's just because we don't have enough experience with it yet. But as it currently looks like is that all our temps ended here in the bottom half rather than in the top part.
Also, we don't use Emacs.
Yes. So by not using, I mean, as long as you're not, Wrangler only really supports Emacs. I mean, there's some other plugins, but if you really want to use the power of Wrangler, you should use Emacs. So those who don't, right, they immediately have a learning curve before they start using Wrangler.
And then there's the little tool called Elvis. Some of you probably heard about it, that does automated code quality checks where you define some rules and say, oh, I want my code to kind of look like this. It's nice. It can check for like obvious things, but it doesn't really prevent bad code. For example, the throwing case exit, that would not be caught in it by any style tool because that's not a style problem. So it's okay. The problem is when you have a lot of old code that probably does not match your style qualities, then you will spend first a couple of weeks fixing it all up so the style matches, and then you can start using it. So that was it. Yeah, I guess if you have any questions.
Maybe we would leave the mic up there. Just so basically, what you're saying, there are no good tools.
No, I mean, it's always the So the question was that there are no good tools. Wasn't really a question; was a statement. That's kind of true. I think the best thing you can do is to prevent issues rather than. I mean, it's really hard to fix issues once you have them. The best thing is to use tools that let you prevent these issues. So if you have a small code base and you don't have a lot of issues, then you can start using Elvis and Wrangler and all these kind of things. You won't need the refactoring quick check because there's nothing to refactor. And then these tools will help you keep it in line. And I think the most important tool is code reviews. We didn't used to do that a long time ago. Now we do it every time. You cannot make a pull request without at least 2 people, looking at it and making sure, okay, that's good. And we've seen a lot of discussions, a lot of arguments in the pull requests, but they all end up actually really well.
Hey, we got any more questions? Anyone else? Okay, you got one over there.
Yeah, so this is a little more of a white box testing, I would say, because you need to understand. Sorry. So the question is, how do we generate inputs for the quick check tests? So yeah, that's not so simple. But we have, for example, when you have a case that can go either way, what we do is we mock out the function that is in the case, and then generate either or output, for example, right? So you have one of each of possible outputs of the case. You need to know the code you're refactoring really well, unfortunately, to use it, right? It's not that simple. But that's also because our code is quite complicated, and if you just generate the first input parameters on top, that may not be enough.
So what I would like to add to that is that when you don't know your code that well, and we didn't in some cases, that profiling really helps. And that can either be by a real profiling tool or by some more specific implementation where you make sure that the inputs you generate cover all paths in your case statement. So you know you can quite easily infer from a function what it can return. So when you make sure that all those values are returned, you know that your cases are covered. And that really helped.
Maybe one thing we forgot to add is it doesn't only check for the output of the function, but also the side effects. So we compare that all the calls to external modules are the same in the new code as in the old code, which means it limits our refactoring because maybe we could have skipped some of these calls, but it's safer because that way we ensure that when we are actually sending, for example, messages to external entities, that they are kept in the same order as they were, because sometimes that's very important.
To me, it seems like you don't trust your test suites and test cases. Maybe you should improve them, and that would enable refactoring much easier.
You got us. You got us right there. Now, the truth is we have a lot of tests, and it's really hard to measure coverage of our tests. So, yes, we don't fully 100% trust our test cases, no.
So I think when you're talking about tests, you also need to think about timing. So the corner cases are usually by the bigger box tests. They're not covered, right? Where you just take your whole application, put something in, and get something out. So to get the corner case, and the corner cases is often where these things get a little bit more tricky, where especially the things that you want to refactor were maybe added there to cover some corner case, and that is why more on a unit test level, this quick checking this really helps, because when you have timing issues, you just also mock a timer, and that way you know exactly that the function matches. So that's why a quick check comparing old and new code is very helpful, even when you have a lot of tests that cover that your big application works as expected.
I work for Ericsson, and we have an extensive function testing based on a common test, where we have the full system inside, and that is really helpful because it helps us.
Yeah, so the remark was that the common test and unit tests in general, I think, are quite helpful to also to test these kind of things. Yeah.
specific question then.
Well,
Is it,
how do you find the concurrency errors?
Alright. Yeah, this will be the last question as well.
Yeah.
It's lunch now. It's quick.
Yes, so the question was, how do you find concurrency errors? I mean, there are many different ways, and for example, with Quick Check, you can do a lot of things, right? Finding. So what we focus on here is where we have a component that works in a specific way, and we just want to make it work in the same way, but nicer. Not sure if you.
I mean, I think in general we haven't encountered that many concurrency problems in our particular application. Maybe that's because the application is a little. It doesn't actually handle millions of transactions or anything like that. In our case, it's a more focus that each transaction really works, because you can't really. I mean, it's maybe a little counterintuitive to Erlang, but we need to make sure that calls go through in the system like that. It's maybe not important that we have a lot of them, but it's more important that each of them doesn't fail. And that's why we also see a lot of these defensive programmings and all of these things, because we need to ensure that this process continues and the call goes on and somebody isn't stuck in a burning building yelling for help. However, we have actually quite extensive test suites that test between the component parts that you mentioned. And normally the problems we find are more of a domain knowledge problems in regards to that, to understanding our protocols and interacting with other components of the system. But that's a little bit outside, I would say. So we like to refactor things internally so we have a little clearer picture, and then we can find where these problems in the code are. Because when things don't work as we want them to between the components, we need to find where to fix it in one of the components. And when the code looks like this, it's sometimes really difficult and takes a long time to find these problems.
I think there was a tutorial yesterday on a tool Conqueror, which messed around. This guy back here messed around with the scheduler and enables you to pin down specific interleavings. Anyway, lunchtime. Thank you very much, guys.